I'll just briefly introduce him. So unlike all other speakers in this very glittering gathering, I actually have vivid memory when our next speaker came into wide acclaim. So I was an undergraduate student, and he, along with his advisor and fellow student, Neeraj Kayal, had proven that for a given number, testing whether its prime is polynomially doable. So that was a momentous result, and since then he's gone on to show many more significant results which have had wide impact in our field. So to recognize him for all his efforts, he's been given several prizes and recognitions, among which some are Gödel Prize, Fulkerson Prize, Shanti Swarup Bhatnagar Prize, and so on and so forth. So without further ado, with great excitement, I ask you to please start telling us about how to factor objects.
Yeah, thank you. So congratulations on finishing 60 years here. I've been visiting IMSC since I was a student. And it's great to be invited here to give this talk. So since this is a very diverse crowd, I'll try to present many things here which I have worked on, and in the most simplest way. I cannot promise that it will be jargon-free, because in my business it isn't possible to make it completely jargon-free, but I'll try. So I'll basically present some algebraic objects and questions, computational questions of factoring them into smaller pieces. So I'll start with what I call base cases. So these are the cases which will be used whenever you want to solve a problem of factorization for any mathematical object. So the first is, well, human beings first defined integers before they got to the level of math which we are used to, right? So integers, you want to factor them, and it is a very important problem. For at least 300 years it has been called by name, and for thousands of years people have given heuristics here and there. So the theorem that starts off factorization is integers can be factored uniquely into primes. Okay, so prime integers are basically those which do not have any interesting factor except 1 in itself. So for example, 1092 can be factored in this way. So 2 appears twice and 3, 7, 13 appear once. So the computational question immediately is, even before computer science was there, even before calculators were invented, this question has always existed, that given n, do you want to find this unique factorization? Yeah, so I forgot to say that important thing is that these numbers here, the primes will be unique. Okay, so there is no other way to factor 1092 except this. So this unique thing you want to find. So the issue is that, I mean, you can just go over all the numbers from 1 to n and check which thing divides and not, because division is very easy. The problem is that once computers came into being, the numbers which are used are very big, right? So numbers actually are given in, the numbers are given in binary, which means that they are given as a sequence of zeros and ones. So if you are given, if say you fill a page, you fill this slide with zeros and ones, then if there are some 1,000 digits, you are basically representing a number which is something like 2 raised to 1,000. Okay, now 2 raised to 1,000, it's just so easy to fill the slide, but I guess even the number of fundamental particles in the universe is much, much smaller than 2 raised to 1,000, right? So you can represent very, very big numbers in very, very small space. And so you don't have enough seconds or milliseconds of whatever to actually do this in practice. Okay, you cannot really just count from 1 to 2 dot dot 2 raised to 1,000. So you have to be more sophisticated. So that is the question. So it's an interesting question. It's a very non-trivial question, and most importantly, it is still an open question. Okay, this is not known how to do this in a practical way. So what is best known is something like 2 raised to number of digits raised to 0.3. Okay, It's a weird complexity to start my slides with. But as I said, I mean, I cannot make it jargon free. So the thing is, you should compare this with the 2 raised to log n. Okay, so 2 raised to log n is just n. So that will be the brute force thing. You just count from 1 to n. So this is just marginally better than 2 raised to log n because it is 2 raised to log n to the 1/3. Okay, so that is the best known. It will be great if you can do something in log n to the 10, for example. Okay, so your target, I mean, after this talk, you should go home and work hard and find an algorithm which runs in log n to the 10. Okay, that would solve an open question. And not only an open question, it will actually destroy your internet industry. Okay, so if you can find an algorithm which can factor in log n to the 10, so it's a minimum $6 trillion industry which you will be destroying. So you should work hard on that. Currently, it's an open question. So this algorithm is called number field sieve. It has many variants. This is just, I think, the best heuristic based on the NFS, which is 2 raised to number of digits raised to 0.3. The idea is very simple. What they do is they try to find two squares whose difference is divisible by n. Okay, so they basically want to solve for x and y such that x square is equal to y square mod n. So mod n will appear many times in my talk. It just means that you divide and you get 0. Okay, so x square minus y square is divisible by n. Why is this helpful? This is helpful because x square minus y square, you know this basic identity that it factors as x minus y times x plus y. So if you have actual x and y, then the difference and the sum will most probably also give you a factor of n when you take GCD. X minus y will share some factor with n, and hence you can factor n. So all you have to do is you have to find solutions for this quadratic equation. Okay, this is what the number field sieve does. It goes to a number field, and then in the number field it finds these solutions x and y. So you have to go beyond integers for this. So you want to factor number integer, but the solution actually goes via more complicated constructions over integers, which are called number fields. Yeah, so the first algorithm was given by Eratosthenes, which is from, I think, 300 BC, which was just go from 1 to square root n and try everything. And from there, we have come to number field sieve, and everything else is an open question. So then it is fair to say, since after 2000 years of work, you haven't found even a heuristic which works in practice. So this problem is potentially a hard problem. So based on the hardness of this, all the internet crypto systems are designed. So whenever you are using HTTPS, you are connecting to your bank, or you are using WhatsApp or Facebook, whatever, the encryption uses the hardness of this problem. Okay, so if you can do this as a homework, then you destroy all this illusion of security in the word. So yeah, so RSA, HTTPS, SSH, SFTP, key exchange, which is Diffie-Hellman protocol, and everything depends on this. By the way, since quantum was mentioned today, if there are quantum computers, then this problem can be solved. Okay, so it's a theorem that quantum computers can factor integers very fast. Okay, so which is why people are investing in in building actual physical quantum computers. But that is also far away in the future. So for now, this is being considered hard. And so it is being used in security protocols. If you have any questions, I would encourage you to ask in the middle. I don't have a big syllabus to finish. I can stop anywhere. So feel free to interrupt me. Okay, so the next thing is, once you have understood integers, then you will want to study functions on integers. So basically maps that take integers to integers, but in the nicest way possible. So those are called univariate polynomials, and you can actually just view them as functions from integers to integers. Uh, so you will be now given those functions, like this function, the polynomial f of x. It has integral coefficients. So let me go to the example. So for example, you have this function which you can think of x as an arbitrary integer, and the answer will be this. You multiply x 5 times, so x to the 5, then you subtract the product of x 4 times, so it's x to the 4, then minus 4x squared plus x minus 2, right? So this is a integral function, but it's not just a function, it's something very special which we call in algebra polynomial, and you can say that this is given in the input. Can I factor it? So again, from the experience of integers, you can prove that polynomials also factor uniquely into irreducible polynomials, which are like prime in this category. So as an example, you can actually find factors of this. I forgot what example I wanted to give. I think the x equal to 2 is a root of this. So if you substitute x2, then you will get 0 here. So in particular, x minus 2 divides this, and in fact, it's a root. The problem is that if you are given an arbitrary polynomial, there is no formula for roots. Okay, maybe you have seen formulas for quadratic equations, for cubic equations, for degree 4 equations. But starting with degree 5 polynomial, there is no formula or no equation, like a closed form expression for the roots. So when you are given an arbitrary input of degree 5, you cannot even find roots, forget about finding factors, because factors may not correspond to roots, integral roots, right? So mathematically this seems difficult. And even checking whether there is a factor or there is a root, even those questions seem mathematically difficult. But interestingly, for this, there are very fast algorithms. Okay, because of these three mathematicians and computer scientists. So his brother Lenstra and Lovash, they found an algorithm which solved this problem completely. So it's actually a deterministic polynomial time algorithm to factor integral polynomials. And hence it can also find roots, integral roots. And it is also fast in practice. So what it does is that the idea is instead of finding integral root or integral factor, you factor it in simpler mathematical objects. Nowadays, it may not be clear to many of you why it will be simpler, because I have not discussed it. But you basically, instead of looking at 4 and 2, you can look at its remainders modulo 2 or modulo 3 or modulo 5. So don't look at the exact integer, but look at some approximation. So this approximation is by division. So you look at the remainders, for example, modulo 2, then 4, then 16, and so on, 256 and so on. So we are moving very fast. So these approximants are getting bigger and bigger as you move forward. But it is still an approximation, because just by looking modulo some number, you may get a factor or you may get a root, but it may not be an actual integral root. But anyways, you do this as a first step. So L cube starts with this, and I have not told how will you do this fast in a practical way, but it can be done. This was already known before this L cube algorithm. So you find those factors, you make them precise as you are moving forward with the approximation, and then at some point you say that I have enough approximation, and you lift it to an actual factor. Okay, so that is called lifting to integral factor, and there something new was invented. A new theorem was discovered by L cube, which makes this precise, and it uses lattice theory. And this is this lattice method which they invented. It is also useful in post-quantum crypto systems. So once quantum computers are there, you cannot use, for example, the first slide. That problem will be solved. So that is not hard anymore. So you will need some other hard problem. So that other hard problem is given by the method which L-Cube invented. Yeah, any questions till now? So this completely solves and creates, completely solves the base case of univariate polynomials over integers, and it gives a theory which is helpful in giving other hard problems, other hard crypto systems. So from here we move to finite fields. So now, basically we will now look at this thing which I was saying that, okay, can I find factors mod 2, can I find factors mod 4 and so on. And in general, can I find factors modulo a prime? Okay, we are now interested in that question. So this comes from Galois. So we call these special fields Galois fields. So I will denote it by GFP raised to E. What this means is it is something like the set of integers, but but even more discrete and finite. Okay, so it is something which we can use in computers, because computers really cannot work with infinite objects. They can only work with finite objects. So for example, in a computer, you cannot truly store e or pi or log of 2 or even square root 2, right? So you just pretend that a computer is working with square root 2, but actually you cannot store it because square root 2 is an infinite, it requires infinite information. So in computers, you need methods which are, again, some kind of approximation, and in particular it should be finite. It should be a small representation. So finite fields or Galois fields are great for that. So it will be a mathematical object which will only have p raised to e many elements. In fact, for this slide, you can just think of e equal to 1. So it will have p many elements where p is a prime, and it will afford all the arithmetic, which is that you can add 2 elements, you can multiply 2 elements, you can take minus of an element, you can divide an element. Okay? So that's a Galois field, and you are given now functions over this. So you are given a univariate polynomial. Again, f of x. X is indeterminate, so it can take any value from the finite field. And I'm assuming here e to be 1, so this is just GFP, p elements. So you can think of p as any prime. Let's say 17. And over that, you have the polynomial. Okay, you can again think of fx as the degree 5 like before. A question is that you want to find factors. Okay, so factorization question over finite fields for univariate polynomials. So as an example, what is the factor of x square minus 2 mod 7? In other words, what is the square root of 2 mod 7? Right, so you can just verify that square root of 2 is 3. Okay, because 3 square is the same as 2. In this weird arithmetic, it's not, I mean, this is obviously false in integers or reals, but this is true in this weird word or Galois field GF7. And again, you can ask whether, whether such a thing even exists. You can ask whether the polynomial that is given to you, is it irreducible, will it have a root, and so on. So these questions are non-trivial questions. And again, the same thing, if you want to do this by first principles, then these will be very slow algorithms, because your polynomials may be very big and your field may be even bigger, right? So the number of possibilities in the whole space is minimum exponential. So you cannot really just try to find it by this definition of factors or by the definition of finite field. That will be too big. So for example, if you are working with 100 degree polynomial over a field which is of size around 100, then the number of polynomials of degree 100 with coefficients 0 to 99 is again something like 100 to the 100, right? And in practice, p can be much, much bigger. So these are actually things which are practically used. So the space of everything is actually very large. So you have to give a non-trivial method. I mean, it is very large, but still finite. In the previous slide, we were working over integers. So there actually the space was infinite. So we previously solved a question which was actually in infinite space. Now the space is finite, but still it's a very big space. You cannot go just one by one because that again will be much more than the age of the universe, 100 times. Right? So those things are completely useless. It's basically an impossibility. So what do you do here? So Berlekamp and Cantor Sassenhaus, they gave fast algorithms. They are very clever algorithms and they are very short. So they are very practical. So these are the algorithms of choice for factorization over finite fields. And what they use is, which is why the photograph, they use Galois automorphisms of finite fields. Finite fields have amazing properties, which is they have amazing symmetry group. So that symmetry group is used. It's something very practical as well. So in just one line, I mean, if it makes sense to you, otherwise you can ignore it. What is done is that essentially you take your input polynomial and you compute its GCD, which means this greatest common divisor, or a polynomial G which divides both f and the second thing. You find that, I should have said how that is found because it's an interesting algorithm. It's possibly the first algorithm in math which was invented. It is present in the book of Euclid Elements, which was written some 2000 years ago. So that gives the Euclid's GCD algorithms, and it happens to be a very fast algorithm. It's an extremely fast algorithm. So that algorithm is used to compute a common factor, the greatest common factor of fx with x to the p minus x. And then you can try that again. If you fail, you try that again with x to the p square minus x. If you fail, you try that with x to the p cube minus x. These polynomials, they have very high degree, but there are tricks to make this efficient. So, but the basic idea, the starting point is this: you compute GCD of f with these things. These are the symmetries of the finite field which I was talking about. There is this Galois automorphism, and it has very nice relation with all the finite fields above FP, GFP. So it has amazing symmetry. So that symmetry is being utilized here. And then there is Euclid's algorithm, which you will do. And there is a theorem or there is a proof that this will work fine. Okay, so mathematically it is beautiful and practically it works very fast. And this is not just a thought experiment, it is being used all the time. In fact, if these things were not there, then computers will not come into being because computers always are making mistakes. Especially when you store information or when you are communicating by a physical wire or by air, there are always bits being flipped because of errors. I mean, any physical system will introduce automatic errors. So if you are sending a long string and even one bit in the string gets lost or switched, for example, your password, right? If you are sending your password, even if a single bit gets changed, then it's useless. So you have to design a system so that, let's say, up to 10% of your bits may get flipped and still your password will make sense. It will be recovered, right? So those things are all algebraic solutions, and that is where such tricks and especially finite fields are used. So yeah, that solves this problem and makes it practical. Next is something slightly more abstract than these Galois fields. These are called Galois rings. So let's see a simple cartoon. So this is the Galois field with two elements. It has only 0 and 1. And it comes with all the arithmetic. So you can add elements, you can multiply elements, you can divide and so on. Okay, so this is the GF2 field, and there are fields, infinitely many fields that sit above GF2, So for example, GF 2 raised to E is there. It has 2 raised to E elements. But it shares something with GF2, which is that 1 plus 1 is 0. Okay, when you add something twice, it's 0 in this object. But it has many more elements. Okay, it has 2 raised to E elements, and E can be taken anything. There are infinitely many examples. So now, what do you want is, can you do the same thing with, for example, mod 4? Okay, instead of mod 2, can you do the same thing mod 4? So there, if you add 4 things, it should vanish. Okay, so I mean, adding 2 things will not vanish, adding 3 things will not vanish, but adding 4 things will vanish. So that is the ring Z mod 4. So is there an analog of this thing? Is there a field which sits above Z mod 4? Now you can show that a field is impossible. So you have to lower your ambitions, and then when you lower your ambitions, you get a precise object, which is called the Galois ring. Okay, so there is actually a Galois ring, an object which sits above Z mod 4. It has elements 4 raised to E, and in it, if you add any 4 elements, it will vanish. Okay, 4 will be an annihilator. And there are these nice maps here. So for example, Z mod 4, any element, if you look mod 2, then you'll come back to the Galois field. And here in GR 4 to the any element, if you take mod 2, then you will go back to the Galois field, which is bigger. So it's a commutative diagram. So this red thing, GR 4 to the E, if you are given a polynomial over that, can you factor it? In particular, if I give you a polynomial mod 4, can you factor it? Okay, so it's not Galois field, it's something more complicated and slightly more abstract. So that's the question now. You are given a polynomial f of x with coefficients coming from the Galois ring of suitable size and dimension. And the question is, can you factor it? So simply an example is, again, you take x square minus 2 in the input. Input you are given x square minus 2, and you have to factor it mod 49. Okay, instead of mod 7, you now have to factor it mod 49. The arithmetic completely changes. Now it could happen that x square minus 2 is irreducible. There is no root, or there may be a root, or there may be many roots. There may not be just one root. Okay, everything here changes because it's a different mathematical object altogether. So, but here you can check that square root of 2 modulo 49 is 10. Okay, because 10 square minus 2 is divisible by 49. And so again, you can ask these questions: is there a root, is there a factor, or is there none? Right? So the question of irreducibility testing. Again, if you go by first principles, it will be very slow. So this problem is currently an open question. We don't know anything better than first principles, which is exponential time. We have some results, but these are intermediate results. We can do this up to k equal to 4, which is mod p raised to 4. And again, we do this in this approximate fashion. We first factor mod p, then we factor mod p square, then mod p cube, then mod p4. We try to look for connections as we make it more precise. But we can do this correctly only up to p raised to 4. For p raised to 5, we don't have a solution. So technically, it's an open question. Why is this the case? Because what the hard case is that there are examples which will look the same mod p. So for example, this polynomial x square minus p is just x square mod p, and this polynomial x square minus px is again just x square mod p. So the difference is actually the part which is divisible by p. So that part in the first example is just 1, it is p multiplied by 1. In the second part, it is p multiplied by x. Okay, so there is a small change happening in the lower order terms, but because of that, the behavior completely changes. So for example, x square minus px mod p square has a root. Obviously, x equal to 0 is a root. But in this case, you can show that there is no root. In fact, it is irreducible. X square minus p, you cannot factor mod p square, although you can factor it mod p. Okay, so the arithmetic has completely changed. And so you have to go deeper into the algebra and find algorithms. How much time do you have? Oh, just 2 minutes. Okay, so that is 1/4 of my talk. Think I did not do too bad. I have done worse. Okay, so then I move to univariate questions over p-adics. So this is Hensel. He invented an extension of this mod p square, mod p cube. He took it all the way to infinity, so p raised to infinity. Okay, so you store this infinite information, and what you get is that you get a new kind of real numbers. Okay, so this is a number system which is in a way completely opposite to the reals. Okay, so in reals, the numbers, I think I have to show that through a picture, but let me first go through the definition. So the elements in this mathematical object ZP, we'll call it, the p-adics, they are actually infinite sums. Okay, so you will always see 1, then p square, p cube, p4, dot p raised to infinity. And then the coefficients here, you can put anything. Okay, so 1, 2, 3, 4, 5 here is just an example. You can put any integers there. So these are your elements. And over these infinite series, you can now do addition and multiplication, and you will again get an infinite series of the same type. So that is the set ZP. It has its own arithmetic, which is very different from what we are used to. And we call these p-adic integers. So these are new kind of integers. And the question is, again, given a polynomial, so basically functions from p-adic integers to p-adic integers, written as in a compact form, which is this polynomial. You want to find roots, or you want to find factors, or you want to check whether they are irreducible. So what happens to x square minus 2 in 7-adic? Right? So you have seen mod 7, there is a number, mod 7 square, there is a number, and so on. So you can collect all those numbers. So mod 7, you got square root 2 to be 3, mod 7 square, you got it to be 10, and mod 7 cube, you will get it to be, 2 times 49, so 98 plus 7 plus 3. So you will get this, and so on. So you can keep doing this. Every time there will be an answer, so you will get an infinite series. Okay, so now square root 2 is actually, you don't have to stop mod 7. You can go on mod 7 square, 7 cube, and so on, till 7 to the infinity. And all these answers are stored here. So now square root 2 looks very much like the square root 2 you are used to in reals. Okay, but this is, so you may want to compare this with base 10. Right, so the square root 2 in base 10 has a certain infinite representation, and square root 2 in base 7 has a certain representation. Take it as a homework exercise whether there is any meaningful comparison. So my claim is that there is none. This is a very different word because, it's very, this is very discrete. So you are actually taking remainders, mod 7 square. So 10-adic, for example, and base 10, they are very different. Okay, so yeah, this is the picture I wanted to show. What happens in 7-adic, the geometry is as follows. So in reals, you are used to thinking that 1 is small, 2 is bigger, 4 is bigger, 8 is bigger, and 16 is bigger. But in 2-adic, it's the opposite. Okay, so in 2-adics, the bigger power of 2 you take, the closer to 0 you are. Okay, so it's an inverted word. So this is called the 7-adic topological space. So, for example, this 10-adic versus base 10, the geometry is very different. So you, the bigger power of 2, for example, here you will take, so 32 will be closer to 0, and in reals, 32 will be further away from 0 compared to 16. Okay, so it's an inverted word, and then here again you have the same questions about factorization of polynomials. And surprisingly, there is a fast algorithm due to Chistov, Cantor, Gordon. And it goes via something called the Newton polytope, coupled with the p-adic metric. So the the 7-adic metric, the 2-adic metric, for example, is that higher power of 2 is thought to be closer to 0. Now, why is that? I mean, if you are confused about this, you have to think about the very first line. So here, this infinite series will make sense only when there is a notion of convergence, right? Otherwise, you know that there will be divergence issues. There will be no single object which will be the answer of this sum. So to get mathematically a well-formed object, which is where this infinite sequence is tending to, the only way is you say that the things which are coming after are smaller. Okay, so p raised to 4 is smaller than p cube is smaller than p square is smaller than p. So with that understanding, you will see that the infinite series makes sense. There is a unique object, unique limit, and so on. So you can do infinite sums now. So that's the p-adic metric. So those things are used in the factorization, p-adic factorization of polynomials. And the base case of this is mod p, of course. So mod p factorization is also used, but then it's very non-trivial to lift a mod p factor to mod p square because it may not lift, as we have seen in examples. So is the time up now? Okay. So if you have any questions, you can ask. Maybe I should just show you what you are missing because of these arbitrary time bounds. Okay, so the open questions are, so we don't know how to factor integers practically. We don't know how to factor polynomials mod p raised to k, where k is bigger than 1. So also p square, p cube is interesting. But the open question starts from p raised to 5. So those were the base cases. I wanted to show you also the cases that come above the base case, which is the case of bivariate polynomials, right? So instead of univariate, now you have 2 variables, or you may have 3 variables, or you may have in general n variables. So for that, there are many representations that we have invented. I mean, meaning in algebraic complexity area, we have invented many representations for multivariate polynomials. So input will be in that multivariate polynomial representation, and you want an output in the same representation. Okay. So factorization in those models. So those are the open questions. Okay, thanks.
Let's thank the speaker, and as a token of appreciation, we'd like to give you a small memento.